Hello everyone. In topic 5 we are going to see the design and the analysis of combinational systems using logic gates. Remember that a combinational system is that for which the outputs only depend on the value of the inputs at any time. The system don't depend on what happens in the past. It's a combinational system. In topic 4 we have established the basis of the digital system. So now I think we are ready for the analysis and the design. Remember that we are engineers, so we are going to have an optimization criterion approach. So what are these criteria? When we designed a system, we have to take into account the cost. It has to be the cheapest possible. The required space. Note that the smaller the circuit, the more we can put in a chip, so the chip can be more powerful. We have to take into account also the response times. The circuit has to be as fast as possible. For this we have to consider that if we have many logic gates connected one after the other, the signal have to go across all of them. So the longest the path, the slower the circuit. More things. Obviously the power consumption, not only from the point of view of money, because if the consumption is high, we are going to spend more money in the circuit when it's working, but also because a high power means a high heat in the circuit. So if the heat that our circuit produces is high, we are not going to be able to put a lot of circuits together in the chip. So the power consumption is another factor that is related to heat. We are going to have several constraints in the design that we have to consider. The maximum fan in and fan out. And fan out. Remember, the fan in is the maximum number of input that we have in a logic gate, and the fan out, the maximum number of output that we can connect to the logic gate. So this is a limitation. We have to respect some interconnection rules. For example, we cannot do this. Imagine that this gate has at its input a 0 and this a 1. You know that 1 is the voltage of the battery and 0 is the ground. So you are creating a short circuit between the battery and the ground. So the circuit is not going to work. And well, we are not going to consider actually these two, but they speak about how easy it is to detect errors or mistakes in our circuit when the circuit is not working properly. So our design goals are using as few gates as possible, using as few connections as possible, and minimize the number of levels. The number of levels appears when we connect one gate after the other. For example, in this circuit, this would be level 1, level 2, and level 3. So if we have a high number of level, the circuit is going to be also slower, as we have seen. So we have to see again definitions and properties if we want to reach the minimal synthesis, a circuit that is the minimal, the cheapest, etc. Well, we have to see as I say, the properties and the definitions. You have here the formal definitions. As usually, I'm going to give you a sample. These definitions are easy to understand. we can say that a function f implies g if for every combination of x for which f is 1, g is also 1. And I think that this is easier to understand just using an example. So, implications. F implies g in which cases? Example. Imagine that we have two variables and we have three functions, three two-variable functions. So for two variables we have 4 combinations, and the functions are like this. And the question is, does f1 imply f2? Yes. Why? Because f1 is 1 in these two combinations. And for these two combinations, f2 is also 1. Does f2 imply f3? So f2 is 1 for these three combinations. So the answer is no, because for this combination f3 is 0, not 1. So no. Does f3 imply f2? So we have to look at f3. f3 is 1 for these two combinations. And f2 is also 1 for these two combinations. So yes, f3 implies f2. I think that this is easy to understand. Okay, we continue with the definitions. We are going to define the concept of implicants as a product term that imply the function. And remember, that means that if there is a combination of the input for which the product term is 1, f is going to be 1 for those combinations as well. Again, we can see it with an example. So imagine that we have the function, the concept of implicant. Imagine that we have this function. So, for example, is x1 an implicant of the function? The first thing, if x1 a product term? Yes, it's a product term because it's a literal from topic 4, remember. x1 implies the function. So if x1 is 1, the function is like this. And if you remember the axioms and properties of the Boolean algebra, something plus 1 is 1. So yes, x1 is an implicant of the function f. Is x1 multiplied by x2 an implicant? It's a product term. So we fulfill the first condition. It's a product term because it's a product of literals of the function. So this product term is 1 only if x1 is 1 and x2 is 1, because it's a AND. It's an AND gate. It's a logic product. So we check the value of the function when this happens. When this happens, we have 1 plus 1. That is 1, as you know. So it's an implicant. More examples. Is s1 plus x2 an implicant? This is easy. No. Why? Because this is not a product term. It's a sum term. Remember, a sum of literals. A sum of literals is a sum term. So this is the concept of implicant. I think it's easy. We have also the concept of implicate. Remember that we have in the Boolean algebra dual expressions. So if the implicant is the product term for which the function is 0, the implicate, be careful because the words are really similar, the implicate is going to be the sum term such that if the sum term is 0 for a certain combination, the function is going to be 0. So we're going to have always dual definitions. I have used red color for product terms and for product terms, blue color for sum terms, and zeros for the dual expression. So we are going to see some examples of implicate. Imagine that we have the following function. It's a 3-variable function. So we have h combinations. H combinations. And the function is like this. It's just an example of function, okay? The function may be different. So, is this an implicant? Remember, implicant, product term. It's a product term, yes. It's a product term because it's a product of literals. The only way of having this equals to 1, because it's a AND operation, a logic product, is that every variable is 1. Remember the truth table of the logic gate AND. So we try what happens with this in the function. So we are here in this combination, and yes, the output is 1. So this is an implicant, yes. For example, this is an implicant. It's a product term because it's a product of literals. And the only way of having this equals to 1, because it's a AND operation, is that the variables take these values. Set have to be 0 because it's a pair complemented, and complemented 0 is 1. So we check the function. We are here, and here the output is 0. So it's not an implicant. More examples. Is this an implicant of the function? No. Why? Because it's a sum term. A sum term. That is a sum of literals. But it's an implicate. It's an implicate. Remember the dual definition. So it's an implicate if this is 0, the function is 0. We have to check it. We have a logic sum. The only way of having this equal to 0 is that this is 0, this is 0, and this is 0. Otherwise, it's going to be 1. So we check the value of the function for this combination. For this combination, the output is 0. So yes, it's an implicate. Remember, an implicate, we use some terms and the output had to be 0. We are in the dual definition, not 1, 0. Implicants 1, implicate 0. So another example. Is this an implicant, an implicate? An implicate? No, because this is a sum term, a product term. It's a product of literals. It's an implicant. We are going to check it. This is going to be 1 only if this is 0, because it's 0 negated, and this is 1. So we are going to check what happens. But we have a special case here because we don't have a value for the variable set. So the variable set can be any value. So we are going to look for the combinations in which x is 0 and y is 1. We are here. X is 0 and y is 1. And we don't care about the value of set. So we have to look at these two rows. And these two rows are 1s. So yes is an implicant. Yes, implicant. And what happened with this, for example? Is an implicant, an implicate? It's not an implicant because this is a sum term. So it's a sum term, can be maybe an implicate. Remember that we are working with zeros now. So the only way of this being 0 is just this. 0 plus 0 is 0. Otherwise, that sum term is going to be 1. So we are going to evaluate the function in this case. And again, we don't have a value for 0. So now we are in this case in which x is 0, 0, y is 0, 0. We are here. And as you can see, for these two combinations, f is 0. So yes, is an implicate. Yes. So just have clear implicants, product terms, and 1s implicate sum terms and zeros. So we are going to continue with the definitions. Well, the things that we are going to have quite a lot of definition in a row. So I think that the easiest way of learning this is just jumping ahead, see some examples, and coming back to see more definitions, because see all these definitions in a row can be hard to understand. So I'm going to jump to the function simplifications with Karnaugh maps. And remember, a Karnaugh map is a method, a tool for representing logic functions in a matrix, in a two-dimensional table. So you have to master this method. You have, for example, this truth table. We have two variables. So we are going to have 4 combinations. We need 4 cells. So we need this Karnaugh map. And remember, Karnaugh map the variables are going to be organized following the gray code. In this case, it doesn't matter because the gray code is the same as the natural binary code. So you have to locate the position of the min terms. This is going to be min term 0 because it's x and y 0, min term 1 because it's x 1, min term 3 here because we have 1 1 for the input combination, and min term 2 that is here. This is important because you have to know how to translate the output functions into the Karnaugh map. Okay, so you have here the correspondence between the Karnaugh map and the truth table. So if you have 3 variables, like in this case, you need 8 cells. So a Karnaugh map with 8 cells can be this one. Remember, super important, the order here to put the variables into the Karnaugh map has to be starting by the most significant variables and following with the rest. Otherwise, your Karnaugh map is going to be different than the method that we are going to use in the class, and it can be messy. You can do it, but it can be messy. So follow my advice, because some errors, some mistakes in the exams has to do with this. So we have 4 variables. We need, remember, 16 cells. So we have 4 rows and 4 columns. Now we are going to see the concept of adjacency. That is going to be a property that we use in Karnaugh maps. So I think that we have the definition here. Just let me check. Well, it's here. Well, I think that is more difficult to see here. I'm going to give you an example. In general, from a general point of view, 2 terms are adjacent if they only differs in one variable. For example, we have this function with 3 variables, a, b, and c, and the function is this way. These 2 terms of the functions are adjacent because they only differs in one variable. C is here complemented and here uncomplemented, so they are adjacent. We can see it as those terms for which the distance is 1. Remember that the distance between 2 numbers is a concept that we show in topic 4. Is how many different bits the number have. So here the distance is 1 because they only differ in 0 and 1. So this is the same for these terms. If we have terms that are adjacent, we can do the following. We can apply here the distributive property, that is the action 4, and make this. And what happens with this? We have the action 5, the complementation theorem, that says that if we have x plus x negated, this is 1. So this is going to be like this. So when we have adjacent terms, we can simplify the functions just using the variables that are the same in both terms. So we can simplify just taking the variables that are the same, and you can check this for every function. So adjacency is a really useful resource to simplify functions. So we're going to see what happens with the kernel map. Remember that in the kernel map, the variables are organized in gray code, and that gray code, its main feature, it does between one combination and the following, the distance is 1, always. So we are going to see what happens, for example, in this, kernel map here. So focus on this cell, the cell of minterm 5. The combination minterm 5 is this combination 0 1 0 1. If we look to the right, we have 13, and 13 is this minterm. If we look upwards, we have 4, and 4 is this minterm. If we look to the left, we have 1, and 1 is this minterm. If we look, for example, downward, we have 7, and 7 is this minterm. So you can see that the distance between minterm 5, that is these cells, and the cells that are nearest horizontally and vertically, the distance is always 1. So you can see that because we have used gray code, the cells that are together in the kernel map are adjacent. And this has happened only in the horizontal and vertical directions. Because, for example, if we take minterm 12, sorry, it's not like this. It's like this. Now the distance is 2. We have this bit different and this bit different from minterm 5. So we can check that in this case, in kernel map, cells that are adjacent in the map are also adjacent from the Boolean algebra point of view. So this is going to be a fact quite useful to simplify functions, because we have seen that when we have adjacent terms, we can simplify functions just keeping the variables that remain constant through all the terms. And this also happens, for example, if we are here in the minterm 10, that is like this. In this way, in this cell, if we look to the left, we are here. Okay, it's like a sphere that we can wrap. So instead, in fact, a cell of minterm 10 and cell of minterm 2 are like adjacent, and you can check it. This is minterm 2, so the distance is only once. So if we look downward, the adjacent is going to be here, the adjacent cell. The minterm 8, that is this, and the distance is once. So it's easy to locate the adjacent cells, the adjacent terms, just looking to the nearest cells horizontally and vertically. And now we are ready to see the following definition. So once we have seen the concept of adjacent cells, we are going to see the concept of allowed group of ones. You can have as well an allowed group of 0. Remember the dual definition. So an allowed group of ones into a Karnaugh map is going to be a square or a rectangle that contains a number of ones equals to 2 raised to n, and each cell within the group is adjacent to another n cells. We are going to see this with an example. So we have, for example, this Karnaugh map with 4 variables. So the function should be like this. Remember, we start assigning the most significant variable here, and we continue. So the rows and the columns and the rows are sorted, following the gray code. So you have to learn from 0 to 3 in gray code. And we are going to see different allowed group of ones here. So, for example, is this an allowed group of ones? Yes, it's a square. I mean, it's only one, so it's a number of cells that is allowed. Is adjacent with 0 cell inside the group, which is obvious because we only have 1 cell in the group. This is an allowed group of ones. Yes, it's a rectangle. It's a rectangle. We have 2 cells that are adjacent with another cell. This one is adjacent with the cells below, and this one is adjacent with the cell upwards. Is this an allowed group of ones? Yes, it's a square of 4 cells, and each cell is adjacent to another 2. For example, this one is adjacent with this one and with this one, and you can check it for the rest of the ones of the group. They are adjacent with another 2 cells. So, more examples. Is this an allowed group of ones? It's a rectangle. We have ones, but we have a problem. The problem is that we have 6 cells. So 6 is not a number that we can get rising to n. So it's not an allowed group of ones. And this. No, because it's not a, I mean, it's not a rectangle, it's a different thing. It's like, you know, I don't know. It's a, but the reason is because the cells are not adjacent. I told you that adjacency appears only in the vertical and horizontal directions. So in this case, we may have a number that is 2 raised to something. Sorry, is 1. But we are not fulfilling this because inside each group, inside this group, this cell is not adjacent with any other cell, and this cell either. So it's not an allowed group of 1. Just one comment. In this Karnaugh map, you are seeing that these cells are empty. In fact, they are not empty. The value for this cell is 0. But when we work with ones, we only draw the ones just to have things clearer in the Karnaugh map. If we draw also the 0, we are going to have a lot of information, and it's going to be difficult to work with the map. So one important thing here is that each allowed group of ones is associated with a product term. So how we can form the product terms? We are going to include in the product term the variables that remains constant across all the cells. Is the concept of adjacency, and we are going to have the dual definition. We are going to have a allowed group of zeros, and we are going to form some terms. So some example here. For example, we consider this allowed group of 1. and we look at the value of the variables. So the variables implies are here. In the columns, the variable that remain constant is x1 because x2 is changing along the group. In the rows, the variable that remain constant is x4. Okay? So how can we form this product term? If the variable is 0, it's going to appear complemented. So x1 is 0, so it's complemented. If the variable is 1, it's going to appear uncomplemented. So this is the product term linked to this allowed group of 1. Is here. We are going to remove this, and we are going to see more examples. For example, this product term here, this allowed group of 1s here. Here we have that the variable that remains constant is again x1, and it's going to be complemented because it's 0. And in the rows, both variables are the same, they don't change. So in this case, we have x1 that is negated because it's 0, x3 that is not negated because it's 1, and x4 that is going to be negated because it's 0. So we are in this case. We are going to see another example, and we continue with more things. For example, now we are going to look at this allowed group of 1, this here. In this case, in the columns, both variables don't change, but in the rows, the variable that doesn't change is x3, that is 1. So the product term associated to that allowed group of 1s is x1 negated because it's 0, x2 not negated because it's 1, and x3 not negated because it's 1. Okay, so we are here in this case. You can practice this at home. I think that is easy, but when you are solving an exercise, it's not enough with finding the allowed group of 1s. You have to make the translation between the allowed group of 1s and the product terms that they are. Okay, so well, we are going to calculate, for example, this. Imagine that we have this here. We have and we are going to group these zeros into an allowed group of zeros. So here, the variable not changing are both in the columns, and here the variables implied in the rows are x3 and x4, and x3 is the one not changing. Remember that with the zeros is the dual thing, so we are going to have a sum term. So the sum term is this one. So x1 is 1, so it's going to be negated because it's just the opposite that's in the previous case. x2 is 0, so it's going to be non-negated. x3 is 0, so it's non-negated again. So this is the sum term linked to this allowed group of zeros. This is just practice. We are going to continue with the definitions. Each product term that is linked to an allowed group of 1s, of each sum terms linked to an allowed group of zeros, is going to be either an implicant or an implicate. I mean, remember that an implicant is this product term, so that if the product term is 1, the function is going to be 1. So obviously we are forming product terms in the ones of the functions. so they are going to be implicant because they are ones. We can see that they are ones in the Karnaugh map, and the function is 1 for these product terms because we have translate this one from the truth table for the places in which the function is 1. So this equivalence is obvious, it's logical. So each product term of the previous example is an implicant because if the product term is 1, the function is 1. We have the dual definition. Remember, each sum term that we obtain from an allowed group of zeros is going to be an implicate because they are zero. We are grouping zeros, and those zeros come from values in which the function is 0. So this is, as I said, an obvious equivalence. We are going to see now the concept of prime implicants. The prime implicants are those implicants that come from product terms linked to a allowed group of ones that cannot be larger. I mean, we can form several product terms, several allowed group of ones in a Karnaugh map with different size. So the one with the biggest size for a part of the Karnaugh map is the prime implicant. And again, this is easier to see with an example. So here, for example, this is an allowed group of 1, so it's a product term and it's an implicant. But this is a prime implicant. These ones can't be covered by a larger allowed group of ones. Yes, these two ones can be covered, for example, by this other allowed group of ones. So this is not a prime implicant. But the bigger, yes, is a prime implicant because it's the largest possible allowed group of ones covering those ones in the Karnaugh map. For example, these two allowed group of ones are prime implicants? No, because we can cover these 4 ones with a bigger allowed group of ones, and this bigger group is going to be the prime implicant in that part of the map. So the prime implicants are the largest allowed group of ones that we can find in the Karnaugh map. Okay, this is as well another prime implicant, for example, and this is another prime implicant. This is in the column, using just the column. Okay, because the largest size that we can get here is 4. So those group of 4 ones are going to be here in this example, prime implicants. So we continue, and we are going to see the concept of essential prime implicants. So they are prime implicants, so they are the largest allowed group of 1 possible, and they are essential because if we don't include these implicants, the function is not covered completely. We say that we cover the function when we include all the ones of the Karnaugh map into an allowed group of ones. If we leave one or several ones out, they are not included in any implicants, the function is not covered. So we have to cover all the ones of the Karnaugh map. The essential prime implicants are those that are compulsory include in the function, include in the sorry, just let me think how to explain this. As the name says, these prime implicants are essential to cover all the function. If we don't use these prime implicants, we are going to leave ones out, ones not covered, and we are going to see an example of this. For example, here I'm going to copy this Karnaugh map to work with it because we have a lot of things here. Just give me one moment. So here we have the kernel map of the previous slide, and we are going to look for the prime implicants. Remember, the largest possible allowed group of ones. So if I look at the bottom part of the kernel map, I can find this one, for example. I'm going to use a different color now. I can find this one. They can be overlapped, it's normal. I can see as well in the upper part of the kernel map this. There is still another allowed group of one that is prime because it has a 4 cell size. That is, for example, this column. Okay, these are all the prime implicants in the functions. We cannot use a 2 cells group of 1 because it's going to be smaller. So this is the largest possible allowed group of ones that we can find here, and we can give them a name. For example, I can give this implicant 1, implicant 2, implicant 3, and the column is going to be implicant 4. Now we do the translation between the allowed group of ones and the product term. So implicant 1 is here, the variable that don't change is x1 and s1 that is 0, so it's going to be s1 negated, and in the rows is x3 that is 1, so it's going to appear not negated. So this is implicant 1. Implicant 2. Implicant 2 is this one. So again is x1 negated because it's the one that remains constant in the columns and is 0. In the rows, the one that remains constant is s3 and is not negated because it's 1 and 1. So we continue. For example, implicant 3, the variable that doesn't change in implicant 3 in the columns is x2, that is 1, so it's going to appear non-negated, and in the rows is x3, that is 0, so it's going to appear negated. And finally, the last implicant is that links to the group 4, that is the column. So in the column, the only variables that remain constant are x1 and x2. X1 is complemented because it's 0 and x2 is 1, so it's going to appear uncomplemented. So all of them are, I'm going to use the other direction, all of them are prime implicants because they are the largest that we can form covering the ones of the function. Now we are going to look for the essential prime implicants, those that are essential. If we don't include this group, there are ones that are not covered. So in order to identify the essential prime implicants, we have to look for distinguished cells. Distinguished cells. Distinguished cells are those cells that contain ones that are only covered by one group. Okay? So cells that are only covered by one group. I'm going to use this color. So, for example, this cell, these two cells here are only covered by implicant 3. So they are distinguished cells. This cell here is covered only by implicant 2. This cell here is not, this cell here, is not a distinguished cell because it's covered by several groups. So the remaining distinguished shell is this one that is covered only by implicant 1. So essentials prime implicant are those covering distinguished cells. For example, if we don't include implicant 3, these two cells are going to be not covered. Do you see it? So implicant 3 is an essential prime implicant. Implicant 1 is as well an essential prime implicant because it's covering this cell. So it's going to be needed to cover all the ones of the functions. If we remove implicant 1, this cell is going to be not covered. Implicant 2 is as well an essential prime implicant because it's covering this one. If we remove implicant 2, this one is going not to be covered. So remember, essential prime implicants, those implicants covering distinguished cells. Okay? Another definition. Well, I'm going to write the definitions because I don't remember if you have this definition in the slide. So cells that only belong to a prime to an only prime implicant. So this is the definition. Okay. So we continue with the definitions. We are going to define the complete sum as the sum of all the prime implicants of a Carnot map. In the sample that we saw previously, all the prime implicants are these ones. So the complete sum is going to be implicant 1 plus implicant 2 plus implicant 3 plus implicant 4. And remember, I can do this because I have defined the product term link to every group of ones here. You cannot do this in an exercise if you haven't done this before. Okay, you can save writing again the expression if the expression are in another part. So this is the complete sum. It's just including all the prime implicants that you find in a Carnot map. Now we are going to see the concept of irredundant sum and minimal sum. The irredundant sum is going to be the sum of all the prime implicants of a function in a way that if we remove some implicant from the sum, the Carnot map is not completely covered. We are leaving ones out. And the minimal sum is going to be the redundant sum that is smaller. We are going to look always for minimal expression because they imply less operations, so fewer logic gates, etc. So they are going to be cheaper systems. So we are going to see examples of irredundant sums and minimal sums. So we have here the algorithm to get the minimal sum or the dual minimal products. We are going to see this with an example. So we are going to work with a Carnot map and we are going to use the previous one. So we are going to obtain the prime implicants of the Carnot map. So the sum with the fewest number of prime implicants is that minimal. So let's see it. We saw that the complete sum is that containing all the prime implicants of the function. How to obtain the minimal sum? We have to look for the essential prime implicants. So the essential prime implicants are implicant 2. We are going to see how many ones are covered with implicant 2. I'm going to use a different color. For example, this one. So implicant 2, so we are going to start with implicant 1, just to have an order. Implicant 1 is here, and with implicant 1 we are covering all these ones. So implicant 1 is here. We start always with the essential prime implicants. So implicant 2 is covering all these ones. Implicant 3 is covering these ones. So are all the ones of the function covered? Yes, they are covered. So we have to include always the essential prime implicants. So if we have include the essential prime implicants and all the ones are covered, this is the minimal sum. And the minimal sum is equivalent to this. I mean, equivalent because the function is the same. They are two different representations of the functions. But you can see that this expression is smaller. In this expression, we are going to need a smaller circuit. So it's going to be cheaper. So the minimal sum, we are going to include all the essential prime implicants, and we are going to check if all the ones are covered. If not all the ones are covered, we have an extra step. We are going to see an example. Well, imagine that we have this example in which they are given us this function. The first thing, this function is expressed how? This is a 4-variable function because we have a 4 here, and we have here a sum of minterms. So this is the compact representation of the canonical disjunctive form. Disjunctive because it's a sum of product term, and canonical because these product terms are minterms. They include all the variables of the function. So we have to translate from this representation to the Karnaugh map. It's easy. We know that in each minterms we have ones in the function. So we have to locate these minterms into the Karnaugh map. The first thing, we are going to assign the variable here in the Karnaugh map, always starting by the most significant variable. We can guess that the variable is like this. For example, you can use another variable if you want. So I start with the W and we continue assigning the variables. So now minterm 0 is here. So we have a 1 here. Minterm 1 is here. Minterm 2 is here. Remember, just have into account the combination here. 0, 0, 1, 0. Sorry, this is Spanglish. 0, 0, 1, 0 is 2. So this is the minterm 2, okay? Just look at the combination formed by the columns and rows. So minterm 3 is here. Sorry, I used the wrong pen. Minterm 4 is 0, 1, 0, 0 is here. Minterm 5 is 0, 1, 0, 1 is here. Minterm 7 is 0, 1, 1, 1, so it's here. And minterm 15 is 1, 1, 1, 1. And minterm 14 is 1, 1, 1, 0, 1, 1, 1, 0. Here. So this is the Karnaugh map. This is how we translate from the canonical disjunctive form, for example, to the Karnaugh map. Not always we are going to start with a truth table. So this is the way. So the first step is to locate the prime implicants of the function, those covering ones that are the largest possible. And remember that they can overlap. We have to detect all of them. So here, if we start by the up part, so we have this product term, for example. We have another one just below. You have to practice, okay, to identify this quickly. we have another one just below. We have as well a column on the left. And we have here, for the remaining ones, we have this one, and we have another one, because there is one that can be covered by two prime implicants with the same size. So if they have the same size, they have to include both of them. Sorry, one of them is this, and the other is this. Okay? Because of this one can be covered by two prime implicants with the same size. So they have the same size, both of them are prime implicants. So now we are going to assign a number, a name, sorry, to each prime implicant. For example, prime implicant 1, prime implicant 2, prime implicant 4, this one. Prime implicant 3 is going to be this one. Prime implicant 5 is going to be this. I don't know, I haven't all. Yes. Okay, now we have names for all the prime implicants. We are going to make the equivalence between the prime implicants and the product terms. Prime implicant 1 is the column, so the variables that don't change are those in the column, that is W and X being 0, so both of them negated. Implicant 2 is we have that W and X don't change because it's a row, it's a column, and both of them are non-negated, so they are uncomplemented. And in the column, in the row, sorry, we have that the variable that doesn't change is Y, and is non-negated because it's 1. Implicant 3 is that square for which we have that W is the one that doesn't change in the columns and is 0, so it's negated. And in the rows, the one that doesn't change is the X, and it's a 1. It's a 1, so non-negated. I have just seen that I have made a mistake here because this is a set. So this is a set, sorry. So implicant 3, the variable that doesn't change is set. Implicant 4 is that one formed by two cells. So in the rows, the variable that doesn't change is the X, and it's non-negated because it's 1 in both cases. Well, in the row we have that Y and Z are 1, both of them, so they appear non-negated. And finally we have implicant 5. Implicant 5 is this square in the upper part. In the columns we have that W is fixed and is 0, and in the rows we have that is Y that is also 0. So the next step, in order to obtain the minimal sum, is to locate the distinguished cells, because we have to identify the essential prime implicants that are going to be included in the function always. So the distinguished cells here are, I'm going to use, for example, black. So this one is only covered by implicant 2. This one here is only covered by implicant 1. We have as well this one that is only covered by implicant 5. The rest of the ones of the functions are covered by more than one implicant. Okay? So we have only these 3 distinguished cells. So when obtaining the minimal function, the minimal sum, we have the following. F is going to be minimally implicant 1, that is this, plus implicant 2, that is this, plus implicant 5, that is this. And now we are going to check how many ones we have covered with this movement. So with implicant 1, we have covered the whole column. With implicant 2, we have covered this half of the column. And with implicant 5, we cover this square in the upper part. So we still have a one that is not covered. So now we have to see how to cover this one. This one can be covered by two implicants. Implicants 4 and implicants 3. Okay? So one alternative can be using implicant 4, that is x, y, and z, and the other option can be used implicant 3. Implicant 3 is negative w and z. And now we have covered all the ones of the functions. So we have here two irredundant sums. Irredundant sums. Irredundant sums are those sums so that if we remove one implicant from the function, we are going to have a ones uncovered. So we cannot remove any of these implicants. If we remove one of them, we are going to have ones uncovered. So the function is not going to be covered and the expression is not correct. So we have here two irredundant sums, which is going to be the minimal sum. Both of them are minimal sums, because if you remember, the definition of minimal sum is the irredundant sum with the smallest number of prime implicants. So if we check the expressions, both expressions have 4 implicants. 1, 2, 3, 4. So both expressions are 4 implicants. Both expressions are minimal sums. So in this case, we have the strictly minimal sum. The strictly minimal sum is the minimal sum with the fewest number of literals. So yes, we have a strictly minimal sum, and it's going to be this one. The strictly minimal sum. Why? Because this sum has fewer literals. If we compare implicant 4 and implicant 3, we have that implicant 3 has 2 variables, so has 2 literals. And implicant 4 has 3 variables, so it has 3 literals. So the irredundant sum, the second irredundant sum, is going to be the strictly minimal sum. This is just see the definitions and apply these definitions to exercise. We are going to do another exercise. So in this exercise we have this function f, we have to simplify it. So we are going to simplify it looking for the minimal sum. Okay? So it's just applying the step that we have seen before. In this case, you have the expression in this form, and you have to translate from this expression to this Karnaugh map. You may build the truth table and just translate the shadow of the truth table into the Karnaugh map, or we can do it directly using this expression. We are going to do it straightforward from here, so you can be faster. Okay, we are going to see this way of doing it. This function, which is form. This is an algebraic form, and if you look at the expression, it's a sum of product terms. A sum of product terms is a disjunctive normal form. Disjunctive because it's a sum of product terms, and normal because the product terms are not min terms, are just product terms. Some of them are min terms, but not all of them. So it's the normal form, not the canonical form. So we know that these product terms are a combination of the input for which the output is 1. Look, we have here a logic product. So just with one of them being 1, the output is going to be 1. Just remember the truth table or the logic product, the OR gates. But it's a disjunctive normal form, so you have here the ones of the function. So we are going to locate the min terms of the function that are related to every product term. So in this case, we have that is negated, w is negated, so it's a 0, y is negated, so it's a 0, and z is negated, so it's a 0. And we don't have the value of the x, so x can be any value. So we are going to be 0, 0, is 0, w is 0 here, here, y is 0 here and here. Sorry, y and z are 0 here, just in this row. So these terms, this product term is here. Okay, so we have ones in this place. So the following term is w is 1 because it's not negated, and z is 1 because it's not negated. Now we are w is 1 here and here, and z is 1 here and here. So we are in these 4 cells. You can see that it's quite fast to do it. So here we have that x is 1, y is 1, and z is 1 because they are not negated. And we are x1 is here, w and z1 is here. So we are in those 2 cells. Okay? You can see that we have some overlap. It doesn't matter. It can be perfectly normal. And finally, we are here. W is not negated, is negated, so it's a 0, and y is a 1 because it's not negated. W is 0 here and here, and y is 1 here and here. So we are in these 4 cells. So we write a 1 inside. Okay, so we have translated from the function in if disjunctive normal form to the Karnaugh map. If you don't have the function in its disjunctive normal form, you can do some algebraic manipulation to have this form. Okay, you already know some rules from the previous topic to do algebraic manipulations, so it's another option that we have. So first step, we are going to locate the prime implicant, those that are the largest, covering the ones of the function. So if we look here in the upper part, we have these 2 ones. These 2 ones can be covered by a 4 cells prime implicants. Remember that we can wrap the Karnaugh map like a sphere. So we can do this. We can group these two ones with these 2 ones. So we have a 4 cells prime implicants. So we can do as well this. We can do for the remaining ones, for example, this. and we still have another prime implicance of 4 ones. That is the row, the complete row. It's a 4 size group, so it had to be included. We had to include all the prime implicants, no matter if we have some overlapping. So we are going to assign names. For example, this is going to be implicant 1. Implicant 2 can be this one, for example. Implicant 3 can be this square. And implicant 4, the column. Sorry, I just mixed the names. And implicant 4 can be the column. The column, not the column, the row. Okay, so now we define the product term linked to this allowed group of 1. Implicant 1 is this one, so here W is not changing and is negated because it's a 0. If we look at the rows, we have that is set, that doesn't change and is negated because it's a 0 again. Implicant 2. Implicant 2 is W non-negated because it's a 1, and Z non-negated because it's a 1 in both rows. Implicant 3. Implicant 3 is this square here. In this square we have that W is 0, so it appears negated, and the one that doesn't change in the rows is Y, that is 1, so it appears non-negated. And finally, implicant 4 is the whole row, so the variables that doesn't change are Y and Z, non-negated because they are 1. So, next step, we are going to locate the distinguished cells, those cells that are only covered by only one prime implicant. So obviously these two that are only covered by implicant 1, and these two that are covered by implicant 2. The other cells are covered by 2 or more implicants. So only implicant 2 and implicant 1 are essential prime implicants because they are covering distinguished cells. The other are just prime implicants, okay? Just prime implicants. All of them are prime implicants, but only 1 and 2 are essential prime implicants. So in order to obtain the minimal sum and simplify the function, we have to include implicant 1 and implicant 2. And we are going to see what happens with the ones. So implicant 1 is covering these ones. It's a really light color. I'm going to use a different one. For example, this. So implicant 1 is covering these ones. And implicant 2 is covering these ones. So we have still 2 ones that are uncovered. So we have to explore the other combinations. We can cover these 2 ones using implicant 3 or implicant 4, that is the whole row. Both options are okay. So we have here irredundant sums 1 and irredundant sum 2. Irredundant sums because all the prime implicants included are necessary to cover all the ones of the functions. So with this, what is the strictly minimal sum? Both of them are minimal sum, but the strictly minimal sum is the sum that have terms with the fewest number of literals. In this case, all the prime implicants have 2 literals, so both of them are going to be the strictly minimal sums, and both of them are minimal sums. So we have solved the function. I suggest you to practice, do the same exercise, but with the zeros, okay? You can redraw the kind of math just including the zeros, and you can work with the zeros and some terms. It's important that you have this present. If you have an exercise in which you have to look for the minimal expressions of the function, you have to check if the minimal expression is the minimal sum or the minimal product. You cannot guess that is the minimal sum. It can be the minimal product. Well, we are going to do it. We are going to do it with the zeros. Just allow me to redraw the Karnaugh map. So this Karnaugh map is just the same as before, but only including the zeros. Now we are going to look for the minimal product. You know, the dual expression. So if we work with the zeros, we are going to look for prime implicates. Okay, the word is slightly different. So prime implicates. We have to cover the zeros with the largest prime implicate, with the largest implicate possible. So these two zeros can be only covered by these implicates, and the remaining zeros can be covered. So you can think that we can use two prime implicates, but it's wrong. We have only one prime implicate covering the remaining zeros. Remember that adjacency is vertical and horizontal, and we can wrap the Karnaugh map as it was an sphere. So we have these two prime implicates. I'm going to call this implicate 1. I use the M to distinguish between implicants and implicate. In implicate I use the M. You can use the way you prefer. Implicate 2. Implicant 1 is going to be this time a sum term. So in implicant 1 the variable that don't change, is W and Z. W is 1, so it's going to be negated because it's the dual, okay, the dual thing. Once negated, 0 not negated. Plus Z, that is 0, so it's not negated. Sum term of implicate 1. Sum term of implicate 2. Now W is the one that doesn't change and is 0, so it's going to be non negated, and here we have the row and we have Y that is 0, so it's non negated, and Z that is 1, so it's negated. So we have these implicates. They are prime implicates. Well, let's see. We are going to look for the distinguished cells. So distinguished cell, all of them are distinguished cells because all the zeros are only covered by one prime implicate. So both of them are not only prime implicate but essential prime implicate. So we have to include them in the minimal product. So the function, the minimal product, is going to be implicate 1 multiplied by implicate 2. Remember that is a product, not a sum. So with implicate 1 we are covering these zeros, and with implicate 2 these zeros. So all the zeros are covered, so we have finished. This is the minimal product. And you can see that in this case the minimal product is smaller than the minimal sum. So the minimal expression is the minimal product, not the minimal sum. So you have to check what they are asking you in the exercise: the minimal product, the minimal sum, or the minimal expression. In the case of the minimal expression, you have to check both of them and choose that one that is smaller. This is another exercise. I just want you to think how many implicants has this function. This is a function that is translated into a Karnaugh map, and I am asking how many implicants does f have. Remember that an implicant is an allowed group of 1. We are not speaking about prime implicants. Okay? Not prime implicant, not the largest possible, just implicants. So we are going to see how many implicants do we have here. So an implicant can be, for example, a group of one cell. So following this definition, we have 1, 2, 3, 4, 5, 7, 8. I mean 8 in total. So we have 8 of this kind. Sorry. 8 of this kind. We can look for those formed by 2 cells. In this case, we have 1, 2, 3, 4, 5, 6, 7, and 8. Another 8. This is an exercise just to see concepts, to remember concepts. So, if we look for implicants of this size, we have only one, this one in the center. So in this function we have 17 implicants. If I ask about the implicants, these are the implicants. If I ask about the prime implicants, you have to look for the largest possible. We are going to look for the prime implicants. The prime implicants, I'm going to delete this, are those that are the largest covered in the function. So in this case, we are going to have this one, this one, okay, this one, and this one. You can check that these are the largest possible implicants covering those ones. So these are the prime implicants. We are going to look for the essential prime implicants. The essential are those covering the distinguished shells. We have here a distinguished shell, a distinguished shell, a distinguished shell, and a distinguished shell. So we have 4 essential prime implicants that are this, and this. So you can see that the Carnot map is a graphical tool that is really useful. We can do things quite fast. Okay, the only purpose of this is just to identify quickly implicants, prime implicants, and essential implicants. So we are going to see a new concept that is well, you can check all the definition. I think that we have seen all the definition so far in the topic. A new definition, a new concept is you have here example to practice, a lot of example to practice in the slides. The unspecified of our don't scare condition. What's the don't scare conditions? The don't scare condition is when for certain, when we don't have the output specified for certain inputs. And I'm going to give you example. We can have the two causes of this. The function definition tells you that we don't have an output for that input combination. I mean, if you don't have an output, it means that the output can be whatever, the one that is more interesting for you as engineer. Or maybe we have combination of the input that are not going to happen ever. So I'm going to give you an example. Things that we have, you find an exercise that tells you that the input of your circuit is one BCD digit. one BCD digit, if you remember, is expressing a decimal digit using 4 binary numbers. For example, one digit in decimal can go from 0 to 9. So you are going to use 4 binary input to specify the number. This is 0 in decimal, and this is 9 0 in binary and 9 in binary. Imagine that this is your, and according to the input you are going to have several values of the output. You have to do the truth table. For example, the truth table, we have 4 inputs because it's a BCD digit. We have 4 bits, sorry. If you have 4 bits, and you are going to have certain value of the output for these combinations. This is 0 in decimal, 1 in decimal. I'm just applying the BCD codifications, etc. until 9. So we are going to have here certain values. Imagine 0, 1, we don't care, just an example. But we know that a BCD digit only covers numbers from 0 to 9. That is the interval of a decimal digit. So what happens with the rest of combination? For example, this in binary. This is not inside the codification of a BCD digit. We don't care about what happens with the combination. Instead, indeed, we are going to write an X in the truth table. Okay? We treat don't care condition just writing an X in those inputs in the truth table. They are going to be inputs that are not going to be present ever in the system, because in a BCD digit these combinations doesn't exist. Okay? So, but even if they doesn't exist in a BCD digit, we can have this in the input. I mean, we have 4 bits, so we don't care about what happens. The output is not defined for this input. Okay? So we are going to see an example of this. How do we treat don't care conditions? These cases in which the output is not specified. Just let me give you an example. So we have this exercise in which we have this function that is provided in its canonical disjunctive form. Remember, a 4-variable function that is expressed as the sum of its mean terms. Okay? But you can see that now we have this. These are don't care conditions. It means that for these mean terms, for this combination of the input, the output is not specified. So we don't know what is the output, and we don't care. Okay? We don't care about the output for this combination of the input. So can we translate this into a Karnaugh map? Yes, of course. So we have a 4-variable Karnaugh map. So we sort the rows and columns using gray code, and we assigned the variables starting by the most significant variable and following with the rest. And now we have ones in these mean terms. So the mean terms 1 is 0, 0, 0, 1. We have a 1 here. In the mean term 2, 2 is 0, 0, 1, 0. The mean term 5, that is 0, 1, 0, 1. This is just counting in binary. It's just practicing, okay? The mean term 6 is 0, 1, 1, 0. 0, 1, 1, 0. That is here 0, 1, 1, 0. The mean term 9 is 1, 0, 0, 1. Is here. And we have included all the ones of the function. Now we have to include the don't care conditions. The name is quite funny, I think. So we have a don't care condition in the minterm temp. The minterm temp is the position 1010. 1010, we have a don't care. So we use an X. We don't know the value. We don't care about the value. The minterm 11 is 1011. The minterm 12 is 1100. The minterm 13 is 1101. The 14 1110, and the 15 1111. Just counting in binary. So this is our resulting Karnaugh map. What we do with the X? The answer is quite easy. We are going to use the X if they are useful for us. So we have to look now for the prime implicants, the largest possible implicants. So, for example, to cover these two ones, we may do this, okay? But we can find a larger prime implicant if we use the X. So we can do this, okay? The X can be 0 or can be 1 according to our interest. So we can do the same for covering these ones. But we can use the X to form a larger allowed group of ones. We may, for example, do this. We may do it. But, well, we don't need it because this one here is already covered. So why are we going to include another group? Do you understand? We are going to use only the X that we are interested in. Okay? No. Sorry. This is not right. If we are looking for the prime implicates, sorry for confusing you. We are going to use the X if we are interested in them. So with this, we have we have covered all the functions. And you can tell me that Andreas, you told me that we have to include all the larger prime implicants. For example, this can be a prime implicant because it's a 4 size cells that is the same size of this one. Yes, you're right, but we are going to consider that the X has the value that we are interested in. I'm going to consider, for example, that this X here are zeros. So I have completed all the function. Using the X, the function is really simple. We have only two prime implicants. This one that is C negated D, and this one that is C non-negated, D negated. So just with these two, we have complete all the function, and the function can be expressed like this. That if you check the truth table of the XOR gate is the same as this. It's an XOR expression. So you can see that using the X in the way we are interested in, we can simplify a lot the function. So every time you see don't care condition, you specify X in the Karnaugh map, you have to cover only the ones, and you can use the X in the more interesting way. If you are working with the zeros, you can use always the X. So for example, we can do this. Imagine that we have this and the rest, and these are zeros. Sorry, I have I cannot remove the ones. I can leave the ones cells empty, but not writing a zero. So we have this, this, and this, because the rest are ones. So again, we can use the x considering them as a zero. For example, to cover these two zeros, we can use the x here, and to cover this, we can use this. So we have finished. Okay. We may use this one. Yes, but you don't need it. If you calculate the minimal sum, you are going to find that this is not needed, because these x are not interesting. So it's it's a resource that we have, and we are going to finish just with an exercise in which we are going to work to find the irredundant sums, having a lot of irredundant sums. So just let me to draw the Karnaugh map. We have this Karnaugh map, and we have to find the minimal sum. The first step is to look for the prime implicants, those that are the largest possible, covering the ones. So we can start, for example, with the one in the middle. So we continue, for example, with this one, covering this one in the top. We can as well see this one covering this one. We have here another. This one can be covered by two prime implicants. For example, this. We have to include all the prime implicants, no matter if we find overlappings. Have this in mind. This one is covered by two prime implicants, because the two of them has a size of 2. So none of them is larger than the other. So we have to include both of them. Have this in mind, please. And we still have to cover the other ones in the right, in the left top corner. For example, this one can be covered by another two size implicants, so we have to include them. I'm going to choose a different color. For example, this is another prime implicant. Okay, and we still have another prime implicant not included before. That is this one covering these two ones, and it has to be included because it's a two cells implicant, so it has the same size as the other ones. It's important that you include all the prime implicants in the Karnaugh map. Otherwise, you are going to have a different result if you are not contemplating all the possible options. So find all the prime implicants in a Karnaugh map is crucial. Now we are going to assign names. For example, this one can be prime implicant 1, this can be prime implicant 2, prime implicant 3 can be the blue one, prime implicant 4 can be, for example, this one, prime implicant 5, for example, this, prime implicant 6, this one, prime implicant 7 can be this, and we still have prime implicant 8, for example, this one. So we have 8 prime implicants. This is a kind of difficult kind of map. So the first step is to find the prime implicant. The second step is to define the product term link to those prime implicants. Prime implicant 1 is the square in the middle, that is x2 not negated, and x4 non-negated. Prime implicant 2 is, for example not, is x1 x2 non-negated and x3 negated. Prime implicant 3 is this one, that is x1 negated, x1 negated, and x3 negated because it's 0, and x4 non-negated because it's 1. Implicant 4 is x1 negated, sorry, sometimes the tablet doesn't work properly. x1 negated, x2 non-negated, we are here, x3 non-negated. Implicant 5 is this one, so in the row we have x4, x3 and x4 non-negated because they are 1, and in the columns we have x1 non-negated because it's 1 in both cells. Implicant 6 is this one, so we have in the column x1 and x2 negated because both of them are 0, and in the rows we have x3 negated as well. Remember that we are including the variables that don't change across the allowed group of ones. Implicant 7 is this one, so we have that in the columns is s1 negated, that doesn't change, and in the rows both of them. x3 non-negated because it's 1, and x4 negated because it's 0. And finally, in the implicant 8 we have that in the columns we have x1 and x2 negated, both of them are 0, and in the rows we have x4 negated because in both cases is 0. So we have defined all the product terms linked to this allowed group of ones. The 8 prime implicants, all of them are prime implicants of the function. So now we have to look for the essential prime implicants. We are going to look for the distinguished cells. In this kind of map, the only two distinguished cells are this one and this one, because all the other cells are covered by more than one implicants. So implicant 2 and implicant 5 are essential prime implicant, and the rest are non-essential prime implicants. Okay, so we have to start to build the minimal sum. Firstly, we are going to check how many ones we are covering with those essential prime implicants, and we are covering these two ones with implicant 2 and these two ones with implicant 5. So we have to still cover the rest of the one that are allowed using the non-essential prime implicants. So we are going to have a lot of combinations possible, a lot of bifurcations. So this is, you have to be really tidy really organized when doing an exercise like this. We know that we are going to start with the essential prime implicants. They are going to be compulsorily included in the function because they cover distinguished cells. And now we start covering the rest of the ones, exploring all the possible combinations. So if we start by this one, I'm going to use this X. We can use, for example, two possible implicants. We can use implicant 1 to cover this one, or implicant 3. You can see it. Okay? So we have a bifurcation. Implicant 1 or implicant 3. So imagine that we use implicant 1. If we use implicant 1, we are going to cover these two, these two ones. So we have to still to cover the remaining cells. So for example, we are going to go to the one on the left. This one. This one can be covered again by two possible implicants, implicant 3 and implicant 6. I'm not going to include implicant 3 because we include implicant 3 in the previous bifurcation, just here. So I'm going to consider only implicant 6. So if I use implicant 6, we have covered the following. We have already covered these two ones. Okay? So now we have to start covering the ones in the bottom part. For example, this one. This one, I'm going to draw it here. This one can be covered again by two prime implicants, implicant 8 or implicant 7. So we have two alternatives. Implicant 7. With implicant 7, we have this covered. So we have covered all the ones. So this is just an redundant sum. We have covered. This is a solution. So if we use implicant 7, we have the first irredundant sum. We have finished the exercise. Not the exercise. We have found the first irredundant sum. What happened with the other combination? If we use implicant 8, we have covered this one and the other at the top. So we still have to cover the other one, the remaining one. Look, note that you have to be really careful, be really tidy when doing this. So in this case, we can use to cover the remaining one implicant 4, and with implicant 4 we have covered all the ones. So this is another solution. Irredundant sum 2. Sorry, the tablet is not really comfortable. And the other action can be used implicant 7. And we have finished. But what happened with implicant 7? I'm going to give you a trick, a rule. If we have used the implicant just in the previous bifurcation, you are not going to have an irredundant sum. So we can discard, we can rule out this theoretical irredundant sum, and you are going to see why. Just following the definition of irredundant sums, an irredundant sum is that sum that if you remove one of the terms, you are not covering the whole functions. So if you can remove one of your terms and the function, and the result is still covering the function, that is not an irredundant sum. In this case, imagine that I remove one term of the solution. I remove implicant 8. If I remove implicant 8, this is still covering the function. Yes, because it's exactly the same of irredundant sum 1. Okay, if we remove implicant 8, we have the result of irredundant sum 1, and irredundant sum 1 is covering the function. So this is not an irredundant sum, not an irredundant sum. And the trick is that we have included this implicant just in the previous bifurcation, so you don't have to include it again. So we have finished all the bifurcation using implicant 1. Now we have to come back and see what happens when using implicant 3. Sorry, it's difficult just to delete this. So now imagine that our solution is to use implicant 3. If we use implicant 3, we are covering these two ones. So we have to still cover this one in the top right corner. To cover this one in the top right corner, we can use implicant 6 here, or implicant 8 that is here. Do you see it? So we are going to explore both possibilities. If we use implicant 6, we are going to cover, we are going to cover this one, just this one. So we have to continue. To cover just let me, sorry, because the tablet is a mess sometimes. So we continue. To cover the implicant to cover the ones in the top part, in the bottom part, we can use implicant implicant 8 or implicant 7 or implicant 7. I don't have space. I'm going to leave this way of implicant 8 here and explain you why later. If we use implicant 7, we have covered these two ones. And to finish, we can use implicant to cover the remaining one. We can use implicant 4. With implicant 4 we have finished, you can see it, of implicant 1, that is the big one. So this is an irredundant sum, irredundant sum 3, and this is an irredundant sum. We have to check it, okay? This is not an irredundant sum. Why? Because if we remove implicant 3, if we remove this, we are going to have irredundant sum 1. Do you see it? If we can remove one term and we have another irredundant sum, we are covering still the function. This is not an irredundant sum. So this is not an irredundant sum. So now we are going to explore what happens with the other possibility. If we use, just let me delete this. If we use S to cover the cell here, the other bifurcation. Imagine that we use implicant H to cover this. If we use implicant H, we have cover these two ones. Remember that implicant H was like this, okay? I just delete the rest of the implicants. And this is the reason why I didn't follow with this path. Okay, because we have a bifurcation just in the previous step, so I know that this is not an irredundant sum, just following the same reasoning of this. Okay, so this is not an irredundant sum. We continue. So we have to still cover these ones, and we can use irredundant 7 or 4. If we use irredundant, if we use implicant 7 or 4, if we use implicant 4, we are covering these two ones, and we have finished. We have a new solution that can be irredundant sum 4. And if we used irredundant 7, it's not irredundant, I'm a little tired. If we use implicant 7, we are covering this one, and we still have another implicant to cover the remaining one. That is here. The remaining one is here. So to cover it, we need to add another one. And we may use irredundant implicant 4 or implicant 1. Implicant 4 was in the previous bifurcation, so I am going to use implicant 1. So this is the irredundant sum 5. You have seen that you have to be really tidy and organized with exploring all the possible combinations. Otherwise, you are going to miss some possible irredundant sums. So it's crucial to identify all the prime implicants and to look for all the possible combinations, just being really tidy. So we have a lot of irredundant sum. What is the minimal? So the minimal that is the minimal sum is that with the fewest number of product terms, of implicants. So we have for example that these two ones, this redundant sum 1 has 4, and irredundant sum 4 has as well this has 5, not 4, 5 implicants, and this has 5 prime implicants, and all the other combinations has 6. Yes, 6. So the minimal sum is going to be one of these two, 5 and redundant sum 1 or irredundant sum 4, which is going to be the minimal, the strictly minimal. Both of them are minimal sum, but the strictly minimal sum is going to be that irredundant sum with the fewest number of literals. If we look at the implicants, we can see that the implicant with the fewest number of literals is implicant 1 because it only has 2 literals. So the redundant sums that imply implicant 1 is going to be the strictly minimal sum and is irredundant sum 1. Okay, so irredundant sum 1 is going to be the strictly minimal sum. So I know that this is quite confusing in the beginning, so just ask me if you have doubts, follow the step, and be tidy. The step. Firstly, we identify the prime implicants, later the essential prime implicants with the distinguished shell. You are going to include in the minimal function the essential prime implicants, and if after including the essential prime implicant there are still ones uncovered, you have to explore if there are ones not covered. You have to include all the possible bifurcations. You have to explore all the combinations to obtain all the irredundant sums. You have to assess, to evaluate where is the minimal redundant sum to obtain the minimal sum. If you have more than one minimal sums, you have to look for the strictly minimal sum, that is going to be the minimal sum with the fewest number of literals. So this is just doing exercises. I think that is a lot. We have finished the class with this. Thank you very much, and let me know if you have doubts.